So we left off on normal distributions in chapter 6, and just to kind of review a little bit, I showed you how to find the probability of a normal curve using plenty of things. I showed you how to find the probability of a z-score less than 1.27 by using the table, right? And this table is in your book. It's in the appendix, table A2. You can find it there. And you just use the 1.2 and the 0.07. That matches up to 1.27, and that's the probability that the area left of 1.27 is 0.898. You could also use, we talked about normal CDF, second varse normal CDF, and you can use this to find the left area. And you could also use the second varse right arrow to distribution draw, and you can put shade norm, and that'll give you the left area as well. And then I had to fix the window to these amounts. I mean, not precisely those, but this is a good window for this normal curve. It fits it pretty nicely. So you do have to adjust the window a little bit if you want to get a better view of it. And then here I just go through the three types. And I never really gone through so much detail on my slides, but inevitably I always get questions on like the calculator keystrokes. So I just decided, you know what, I'm going to do it once and for all, but put the slides on here. So this is left area of a z-score, 1.45. You're going to put lower bound from negative infinity to 1.45 to the z-score. And it's a standard normal curve. The standard normal curve is 0 and 1, so you just put 0 and 1. And then you push enter, and then it'll give you the probability. It won't necessarily draw this for you. If you want that, you need to go do the shape norm. But I usually just do normal CDF. I don't usually draw it because normal CDF just gets you the probability of the left. If you want probability of the right, well, this time we want the right of the z-score of 1.45. So that's 1.45 would be here, and to infinity. Remember, the calculator doesn't register infinity. There's no infinity button, so you have to type E99. It's a standard normal curve, so it's mean of 0, standard deviation of 1. Also here, we want the probability or the area, which I don't know if we talked about too much, but area and probability somehow coincide. Okay, so there's more to it, but for now, I'm just going to say that the area does correlate with the probability of two events. In this case, between two z-scores, and then we'll kind of get into kind of some real situations using this. But that's how you're gonna find it. And I think we should have. I think I showed you an R, right? So you can just do P norm right there. P norm 1.45. That gets you the left area. Now R only does left area, so you have to kind of coerce it a little bit. So P norm would be over here in white or gray, I guess. The area in gray under the curve. And the whole entire area of the curve is 1. So 1 minus the P norm of 1.45, the area in white, is going to give you the area in orange. So that's how that works. Over here, the P norm, if 1.45 is right here, then what P norm is going to do is get you the area left of that. And what P norm of 0 is going to do is going to get you the area. So P norm of 1.45 gets you the pink plus the gray area. P norm of 0 just gets you the gray area. So if you take away the pink plus the gray area minus the gray area, you're left with the pink area. Because again, R only does left areas. So this is how you'd have to do it in R. But I think the calculator is nice, convenient. However, this one's kind of nice and convenient too. It's kind of less effort, I think. Versus this one, I have to push maybe about 6 buttons. Over here, I just type straight P norm 1.45 and I'm done. Well, I have to type like 6 entries in here. But anyways, so we're gonna practice out a little bit more. So I have here an example. So the probability of z is less than 2. which is the same as asking, and I didn't really put too much work on this slide because I wanted to work in class on it. So what does this mean? You could always draw a picture, and remember that zeros in the middle. Usually they label 3 to the left because most of the data is going to be contained within 3 standard deviations. -2, -3. Okay, so in this case, the area to the left of this, if I draw a picture, is going to be from -2 below. Okay, so I'm interested in that probability. In order to find that probability, I can simply do normal CDF. So second vars, normal CDF, negative infinity to the upper bound, which is -2. Okay, and we get an answer here. It's 0.0227. So 0.0228 actually, if I round. So that's the probability that a z-score is less than or equal to -2 on a normally distributed curve, a standard normal curve. The second question here, we're interested in that it's greater than. So I can do 0, 1, 2, 3, and then -1, -2, -3. And then we can also get away with doing less detail on this. So I could just kind of put a line here and label it -1.23. Usually I do it at the bottom, but I'm going to do it up here now for space. Okay, so -1.23, and I'm interested in the area that's greater than. So that's the picture of this. And it helps, and sometimes I'll ask you to draw the picture, but not always. When I was in class in statistics, all those years ago, I remember drawing about, geez, it must have been like 500 normal curves at least. So I drew tons of normal curves on my notes, my homework, but it just helps you to understand, especially your bounds. I think it helps you understand your bounds. You're going from -1.23 to infinity. And then there's other reasons, but we'll get to that. So here, the probability of the random z-score is less than 1.23 equals to 0.8907. Okay, and then the final one is the probability. We want to find the probability that this notation here, maybe we don't see too much. Okay, you gotta excuse my twos. Sometimes they look like Z's. This is the area, and I guess I should be, okay, I think this is the area between the 2 points, okay? So if I draw a picture, this time I think I'm gonna take my advice and do a little less detail, but you should know some basic things. Zero's in the middle, so one's gonna be like about here, and then 2 would be somewhere out here, okay? So those are z-scores, and this is the z-axis, right? They're all z-axis right here. So I want this area from 1 to 2, okay? And in order to find that area, I still do normal CDF. Now, in the calculator, it's pretty straightforward. Normal CDF from 1 to 2, right? But you know, before I put the answer, I want to draw your attention to something real quick. Let's recall that we talked about this rule, the empirical rule. Okay, and this time I am going to draw the detail 1, 2, 3, meaning just labeling up to 3. Okay, -1, -2, -3. Okay, so the empirical rule says that within 1 standard deviation, you have 95% of your data. Within 2 standard deviations, you have 90. Oh my goodness, I think I forgot. Here, give me. Okay. Backtrack. It's because I messed up on the first one. It's 68% of the data that you have in within 1 standard deviation. Okay, so I just had a little brain freeze there. It happens when I don't have my coffee. It's sitting right next to me, but I haven't had the time to drink it. Here's 95% within 2 standard deviations, and then within 3 standard deviations, you have 99.7% of the data. Okay, so why do I bring this up here? Because that means if within 1 standard deviation is 68%, half of that's 34%. Okay, and also if within 95% is 2 standard deviations, half of that's 45%. So if I take each of those halves, like the 45 from 0 to 2 is 45, and then from 0 to 1 is going to be 34. I'm sorry, 0 to 1, yeah, is 34. So if I do 45 or 40, it's not 45, it's 47.5. 47.5 minus 34. That's going to give me the same probability that we'll see here. So that'll give me about 13.5% or 0.135, I should say. Well, I can put it as percent and then change it, 0.135. Okay, but let's see what the actual probability is. That's a pretty good estimate, but you'll see it's roughly the same. But that's using the empirical rule. Okay, and you can use it in several ways. But that's just something I draw to your attention. Your normal CDF is fully available to you. Okay, now there are some other cases when that I'm just going to go here, and we'll have some examples to follow. In these problems, the previous slides 8 and 9, you're given a z-score and you want to find the area to the left or to the right or in between that z-score. Now on these problems, now you're given an area, and you want to calculate a z-score for that area, whether it's a left-tailed area or a right-tailed area. So in this case, you're not going to use normal CDF. We're going to need to use something else, which is inverse norm. And I think we covered it, but I think I didn't talk about the table. So inevitably, I guess every semester I have somebody that likes the table, which is fine. But if you want to use the table, then instead of doing inverse norm, obviously you're gonna look at the area. The area is 0.5, so it's a left-tailed test. So the area is going to be on the left side, and the table only does, kind of like your calculator. The calculator only does left area. Well, at least most of your calculators will only do left area. So the table is the same. So I'm looking for a left area of 0.05. However, it's a little impromptu. I don't have it, but I'm going to show it here. I should have this table here somewhere. There we go. All right, so if you look, I'm looking for a table like this. Your book might have a slightly different table, but it's pretty much the same. You're looking for in the body now, not the borders. You're looking for in the body 0.05. So I'm just going to kind of scan until I get 0.05, or the closest thing I can to 0.05, which what I'm seeing is probably around here somewhere. And it turns out it's actually in the middle. And it turns out actually 0.05 is, you'll see, is a special case. Well, they don't say the special case here, but okay. Anyways, let's look at it's going to be negative 1 point. It's like perfectly in the middle of these two numbers. So 1.60, 1, 2, 3, 4, 5. So negative 1.65. But if it's perfectly in between there, you can actually say negative 1.645. Okay. So that would be the z-score that correlates with that. Okay. And yeah. So that would be the answer there. Using the table, which I think what we got was negative 1.64 using the calculator, right? And for the calculator, you just do second vars inverse norm, second vars inverse norm. But the big deal here is just inputting the correct area. This first one was a left tail test, so you just put the left area, you just put the alpha, the area, okay, and that's what that gives you. Now, and on the table as well, you have to put in the correct, or you have to look for the correct thing. So you'd have to look for 0.95 for a right tail test. And why? Because the area here, the left area is going to be 0.95. Okay, because the right area is 0.05. So to find this z-score right here, you need to do inverse norm of 0.95. And then finally, your area of alpha over 2, or your two-tailed test. And I think the picture is kind of hard to see here on the bottom of this, but your two-tailed test it is going to look like this, and that means the total area on both sides is going to be 0.05. So that means each side divided by 2, you get 0.025. Therefore, to find this z-score, you're just going to do inverse norm of 0.025. So for a two-tailed test, you're going to do the area divided by 2, or the alpha divided by 2, and then do inverse norm of that. Okay. So these I'm emphasizing again, going over it again, because these are going to be important. Just like these are going to be important. Okay. So these two slides you might want to come back to, or just you want to know the content on here pretty well. It's going to help you out with the rest of your work for this section and kind of mini sections to come, actually. So these you might want to know just at heart. And I would always get questions on the calculator keystroke. So this semester I just decided I'm gonna put them on there. There's no question. You can always go back to it. There's no need to struggle. Okay. And then also, if you want to use like the R, that's available too. Okay. And kind of using the same thing, the same alpha areas, and also kind of less hassle, I think. But I'll leave it to you. You have your calculators, and you have R. Okay. So let's start answering some questions with this information. Finding area to the left of a z-score, a bone mineral density test, can be helpful in identifying the presence or likelihood of osteoporosis, a disease causing bones to become more fragile and more likely to break. The results of bone density test is commonly measured as a z-score. The population of z-scores is normally distributed with a mean of 0 and a standard deviation of 1. So these tests meet the requirements of a standard normal distribution, and the graph of the bone density test score is shown in figure 6.5. So there's no figure because I'm going to have us draw it. A randomly selected adult undergoes a bone density test. Find the probability that this person has a bone density test score less than 1.27. So I'd like you to draw stuff. Okay, so we're gonna try drawing it. I'll leave it at that. So we're going to do a normal curve. And I'm interested in a z-score less than 1.27. So if 0's in the middle, then 1.27 might be somewhere about here. Okay, and so I'm interested in the area to the left of this. So I'm just going to kind of shade that area. Okay, and that's my goal. In terms of notation, I want to write the probability that the z-score is less than 1.27. That's what I want to write. And now we calculate second vars, normal CDF. This is going to go from negative infinity, so negative 1 E99 to 1.27. Okay, and then push enter, and I have an answer, 0.898. That's it. So the probability that somebody has a z-score bone density test of 1.27 is 0.89808. So there you go. That's a direct application of these normal z-scores, the bone density test. Because any random person or a distribution of random people would have this distribution of bone density. And again, the normal curve, I don't think I really got into the normal curve that much last time, but you have, it's this idea that most people fall in the middle. Few people fall in the extremes, which happens a lot. For instance, like heights, most people are pretty average height. You have few people at the extremes, right? And it starts tailing off. Like you got your, you have 6'2", 6'3", 6'4", 6'5", 6'8", 7 foot, so there's not as many 7 foot people as there are going to be 6 and maybe 5'5", kind of average height, 5'8". Maybe if we just talk about males, and then also at the same token, you have some people that are like 5'4", and 5'3", and 5'2", and 5'1", but you're not going to have a lot of people like 4'8", 4'7", 4'6", 4'5", and so forth. They're there, but they're just not as much. So that's this idea of a normal curve, and it just so happens that happens here with bone density, right? Most people have an average bone density of 0 with the z-score, and it'll kind of tail off as you get closer to 3 and beyond, and then tail off as you get to -3. Okay. So same with the bone density situation. I'm just going to kind of jump to the question here. It says find the bone density score corresponding to the P95. This is the 95th percentile. So we want P95. So I'm also going to draw a picture with this. So P95, referring to the normal curve again, indicates a left area of 95%. So percentile is always left area. That's important to note. So that's left area of 0.95. So I have an area, I have a percent, which correlates to an area. So I want to find the z-score that correlates to that area. Which, just a little on notation, percentile means left area. And in other words, we're looking for the z-score that correlates with left area 0.95. That's what this notation means. So again, inverse, we're going to use, if we have an area, we want a z-score, we use inverse norm. So that's the area, and we're going to do inverse norm. So inverse norm, second vars, inverse norm, 0.95. And right now I'm not going to mess with the mean or standard deviation because it's standard normal curve z-scores. Anytime you use z-scores, you just leave it at 0, 1. And we actually did this problem, right? 1.645. Okay, so that's the z-score. Also, that's the cutoff between the bottom 95% and the top 5% of bone density scores. Is a 1.645 is the z-score that cuts off the bottom 95% to the top 5%. Okay. It says use the same bone density test from example 3. Find the probability that a randomly selected person has a result above -1. A value above -1 is considered to be a normal range of bone density readings. So above -1, which I have, I don't know if I'm using my, yeah, I think I might be using my older slide. Give me, because I think I updated these. So I think what you have online, you have more, but it's pretty much the same. I just put more in the answers. Anyway, so here, I'm interested if zero's in the middle, the -1 is going to be about here, right? Because this will go up to about 3, where most of your area is. And I want the probability that it's above. So we're just going to get that area. Okay, so the probability that z is greater than -1. Okay. So let me answer this without doing a calculator. If within 1 is 68%, outside of that is 32%. So then half of that is 16%. So this is 16% right here. If the whole area curve is one, then I can use 1 minus 0.16, and I'll get my answer, okay, which is going to be 0.84. Okay, but let's see. You don't believe it? We can try it. Second vars, normal CDF from lower is -1 to upper is going to be infinity. .84, right? So the logic works, but that's the empirical rule, and I think I had more on that somewhere here, but here's the breakdown. Okay, within is 68%. Well, they kind of get more detail than I did. The book I think uses 68%, not 68.3. But outside of that would be the 32%, or half on this side would be, or outside of this would be 32%, half would be 16% over here. And then 1 minus 16 is the 84%, which is 0.84. Okay. So that's that. Here is just a matter of notation, just teaching you this, what this means. That just means the area to the left is of this z-score is, so anytime they have the notation here, that's the left area. Okay, so they're telling you find the z-score with the left area of 0.025. Okay, which we've done. We're just going to do inverse norm again. So second vars, inverse norm. Second vars, inverse norm. Of course, you could search the body of the table for 0.025 as well and get the z-score that correlates with that. Mean is 0, standard deviation of 1. You get -1.96. And this is one of those common ones you'll notice that comes up. You're going to see that certain z-scores come up more than others. Okay. So find the bone density test score that separates the bottom 2.5% and find the score that separates the top 2.5%. Well, it's kind of an extension to this question because we have already found the bottom 2.5%, the 0.025. Who could tell me? So here's a question for y'all. If I want this z-score right here, does anybody know the answer to that? What is a z-score on the opposite side? Good. So Lauren says is it just a positive number? That's right. Yeah. So this is symmetrical, right? So zero's in the middle. This -1.96, so the other side would be +1.96, which is going to help because a lot of times you'll be asked to do a two-tailed test, and it'll have equal area, so it's easier to do just the opposite instead of. You could also do the area to the left of this is going to be 1 minus 0.025, which is 0.975. You can do inverse norm of that left area, 0.975. And it'll give us the same thing, 1.96, the positive. But however, if I can, I'll type less. I'll try to type less and just use symmetry. That's a lot easier. Okay, so good to know. Those z-scores we just calculated, so for a normal distribution is a critical value, or a critical value is a z-score on the borderline separating those z-scores that are significantly low and significantly high, which is a little bit different, right, from what we've talked about. Although before we talked about significantly low and high as 2 standard deviations above or below the mean, or in other words, a z-score of -2 or 2. But this one's telling us 1.96. Which the 2 still holds, right? Because if you're 2 and beyond, you're still beyond this. So nothing is broken by this new rule here. But now that's what they're using as a common. They're just telling us this is a common critical values, and then we're going to learn that the critical values are kind of change according to the researchers. So, and we'll talk about that more later on. But so they set a critical value and they say, okay, beyond this or after this, this is our critical value for this experiment. But I won't get too much into it right now. And here we would say 1.90, anything beyond 1.96 is significantly high because only 2.5% of the population have scores at or above 1.96, which is less than the 5%. So the rules still apply that we've talked about before, the beyond 2 standard deviations and then the less than 5%. Okay, so for the standard normal distribution, a critical value is a z-score on the borderline separating those z-scores that are significantly low or high. So that's what a critical value is, to separate whether something's significantly low or high. All right. Okay, so 6.2. Before I move on, I think what I'm going to do is I'm going to search for my intended PowerPoint because like I said, it's not much different, but just in case somebody downloaded it, should be this one. Yeah, this one's a little bit more work done. Okay, so let's go ahead and start 6.2. So we haven't really calculated a z-score yet, but there is a calculation of it. Here it is, x minus the mean divided by standard deviation. So fairly straightforward, but here's a non-standard. So far, actually, we started here on B, which is standard normal distributions, which are distributed with, we can write with a mean of 0 and a standard deviation of 1. So this means that this curve is normally distributed. That's the n. The first number is the mean of 0 and a standard deviation of 1. Over here, more realistically, most things don't have a mean of 0. They're going to have a mean of whatever it has, the mean, and it'll be distributed with whatever standard deviation it has. Okay, so this is a non-standard normal distribution. However, there are ways that we can transform this to a standard distribution, because I just showed you how to work with the standard distribution, and I just showed you how to find probabilities of a standard distribution. So we're going to transform from a non-standard to standard, and then we'll be able to calculate probabilities with that. So with that said, what are we going to do? Sketch a curve just like we've been doing, shade the region that you want the probability of, and then for each relevant x that you're interested in, calculate a z-score, and then we'll use technology to find the area. And then I'll show you that you can skip step 2, where you don't really have to calculate a z-score. However, you should know how to calculate a z-score because it will be asked in different ways. But I'll show you the shortcuts, but I also expect you to know, kind of the logic behind all these steps and how to calculate a z-score in this case. Okay, so here we have a question on post rates. We noted that post rates of adult males are normally distributed with a mean of 69.6 and a standard deviation of 11.3. Find the proportion of adult males with a post rate greater than 100 beats per minute. Okay, so we're gonna draw a picture. It tells me it's normally distributed, right? So I'm just gonna draw a normal curve. And that you have to pay attention to, because if I didn't go over today, but if a question says uniformly distributed, obviously you're going to approach this a lot different because uniform is a rectangle, like we talked about in the beginning of last class, or the beginning of this chapter. Okay, so it says the mean is 69.6. I can put that here. And then it'd be nice to label at least 69.6, comma 11.3. Just saying what it is, or I think maybe more appropriately for y'all for now, since we just started, we'll just write mean of 69.6 somewhere and standard deviation of 11.3. And we're interested in that the pulse rate is greater than 100. So we're gonna put 100 somewhere out here, and we're interested in the area beyond that, right? Because it says greater than. Okay, so here's a question. What function would we use? Normal CDF or inverse norm? So N for normal CDF or I for inverse norm? Okay, good. So I have N for normal CDF from a couple of y'all. So let's do that. And before we do that, though, we're going to have to calculate a z-score. So z-score, because that's what we did in the last section, right? We use z-scores. So if I use the z-score formula, I will get my value of interest is x equals 100. So I'm interested in that's beyond 100. So I'm going to do 100 minus the mean, 69.6, divided by the standard deviation. We'll do a quick calculation of that. Okay, so 100 minus 69.3, or 6, sorry, divided by 11.3. That gives us 2.69. So, and here's the notation. The notation is the probability. I'm actually interested in the probability that x, right? Because this is an x-axis. But like I said, we're going to transform it, and I could draw another one, but here I do this sometimes. I kind of put the transformation here on the same axis. The z-score, the middle is 0, and I just calculated the 100 as 2.69. Okay, so I kind of have two axes here. X is like the real axis of pulse rates. Z is our standard normal curve that we changed this 100 to. The mean is always going to be 0 for the standard normal curve. But now I know how to calculate this. But let me finish the notation here. So I'm interested in the probability that x is greater than 100, which is equal to the probability that z is greater than 2.69. Okay, which now I know we're going to do the normal CDF of that. Normal CDF of 2.69. E to 99. So I get 0.0036 is my answer. So the probability that pulse rates that a random pulse rate is greater than 100, that one male or one adult male's pulse rate is greater than 100 is going to be 0.0036. In other words, it's less than a 1% chance, or a 0.36% chance. Which tells you if you get somebody with 100 beats per minute in a hospital or something, then it's definitely an emergency, right? It's an unusual event. Okay, so find the percentage of males with pulse rates less than 60. Okay, similar questions, so we'll go through it a little bit faster this time, but here, same thing. Mean of 69.6. That means 60 is going to be somewhere about here. Okay, and I'm interested in that the proportion of males, or the percentage of males less than 60. So my notation is the probability that x is less than 60. If x is represented as pulse rates. And but before that, I do want to calculate. Yeah, let me do that first. Let me calculate the z-score. Okay, so z-score equals to x minus mu over the standard deviation. This time x is 60, so 60 minus 69.6 divided by 11.3, which I can just be I won't say lazy. We'll just be we'll be efficient. Okay. Another word for no, efficient's efficient. Lazy is lazy. Okay, so this is not working. How? There we go. Okay, so let's just change it to 60, and there we go. Negative 0.8496. 96. All right, so that gives me my my solution there, or the z-score actually. So now I got to write the solution. So here I get the probability. The notation would be probability that x is not greater than, less than 60 is equal to the probability that z is less than negative 0.8496. And then I can calculate that using normal CDF. So second parse normal CDF of negative infinity, negative E 99 to negative 0.8496. And then we push enter. And you get 0.1978 as your solution. So there you have it. That's how you find that probability. Convert the x to a z-score, given the mean and standard deviation for both. And so this one we had area to the right. This is area to the left. And I think I have one more. So this one says normal pulse rates are generally considered to be between 60 and 100 beats per minute. Given that pulse rates of adults are normally distributed with the mean of 69.6 and a standard deviation of 11.3, find the percentage of males with the normal pulse rates. So these are normal pulse rates. Normal pulse rates, okay. So again, draw a picture, right, because it's going to help guide our thinking, I think. And we're going to do the normal in the middle, or the mean in the middle, 69.6. And 60 again is a little bit below. 100 would be here. And we want to find, we're interested in finding this area, is what they consider normal. Okay. All right. So this time we're going to have to find two z-scores. So 60 minus 69.6 divided by the standard deviation 11.3. Also, we're going to want to find the second z-score of 100 minus 69.6 divided by 11.3. Okay, so we're going to go ahead and do those two here. So 60 minus 69.6 divided by 11.3 gives us negative 8.496. Yeah, and I guess if I think about it, I really don't have this work to do because we've actually did these already. So the z-score is for 100 is 2.69. So I guess I won't redo that work. Oh, I already did. So I'm just gonna put the answer. So it's 2.69. Okay, so that's the z-score. We really didn't have to redo it, but here, what's the notation? So I'm interested in that the x is between 60 and 100. That's how you'd write it. This literally says that x is between 60 and 100, but if you read it, 60 less than x less than 100. In terms of z-scores, well, now I put the two z-scores and the z in the middle. Okay, and from there, I just calculate normal CDF. So second var's normal CDF is going to be negative 0.8496 over 2.69. And I get 0.7986. 87 if I round up. And the nice thing about drawing, here's the other thing with drawing the normal curves. So if you draw them somewhat accurate, you should kind of say, okay, that's about, yeah, I buy that. That's about close to 80% of this. So they're good as also logic checks with your answers. Okay, and let's see if the other ones kind of match up too. So this one's 0.0036. Yeah, I probably should have drawn less area here, but I could still buy it. That's about less than 1%. But the picture I can tell is going to be a little off. Here, 20%. If half is like 50, okay, I can kind of buy that. That's around 20%. Okay, so it just gives you kind of a roundabout estimate of the area. So in other words, what it really helps with is if you say, if you got an answer of 0.7, then you would say, okay, well, that's not half the area, so I think there's something wrong with my answer. Something wrong with my answer you're drawing, but hopefully it's something you can figure out. But it'll just draw your attention to it. Okay. Now, with the same problem, now they're given the post rate of 69.6 for the mean and standard deviation of 11.3. Find the post rate that separates the highest 1% from the lowest 99%. In other words, find P99. Okay, so inverse norm or normal CDF, I or N? Still got to draw a picture either way. What do y'all say? So let's just say 1% over here. So that's a question for y'all. Inverse norm or normal CDF? Okay, so let's talk about it then. You have an area / probability, then you're probably going to want to use, and you want to find a z-score. That's inverse norm. If you have a z-score and you're looking for a probability, or yeah, probability usually. I guess you could say area / probability as well. But usually questions don't ask for areas; they'll ask you for probabilities. Then that's normal CDF. So that's how you'll know. Okay, which this is very important. If you can get this down, plus those two slides I showed you, now you should be able to kind of go through the homework pretty quickly. So I'd spend some time looking at those, and then you're going to speed up your work tremendously, I think. All right, but this is inverse norm. Okay, so you need to do inverse norm here. So second vars, inverse norm of the area 0.99, and you get 2.33. That's the z-score. And why 0.99 rather than 0.01? Because that you have to use left area, whether you use the table, whether you use the calculator, or even if you use R, right? Because R I can use. Let's try R here. I can use Q norm of Yeah, so I got a whole bunch of mess here, but just Q norm of 0.99. Yeah, 0.99. That'll give us 2.33. The same thing, which are pretty clean and efficient, and just calculating without much hassle. But the calculator is not that bad. Yeah, I mean, it's roughly the same work. So my answer here is the z-score is 2.33, but actually that's not quite the answer yet. I know the z-score for that cutoff is 2.33, but we're interested in the x value. We still don't know the pulse rate. We don't know the pulse rate that cuts off the bottom 99%. So I can put the z-score into this formula, 2.33. I don't know x, but we do know the mean, and we do know the standard deviation, so we can do a little bit of algebra and solve for this. So if I multiply both sides times 11.3, I'm left with this, and I'm not even going to calculate yet. I'm just going to do the final step, which is I would have to get x by itself. I'm going to add 69.6. So plus 2.33, and that's how I'm going to type it in. So there, that would give you my answer for the pulse rate. So 69.6 plus 2.33 times 11.3 is 95.929. Okay, so that's how you calculate the x value, or the pulse rate at the 99th percentile. So in other words, in terms of this question, 95 beats per minute would be the 99th percentile. In other words, that's the cutoff from 99% of the people would have lower than 95 beats per minute. Okay, so I've been holding out on you, and I've been kind of making you do the z-score, but like I mentioned here, I'm going to show you a way without having to convert to a z-score using your calculator. So we're going to redo all these problems, but really quickly. So here, however, let me emphasize again, you should know how to calculate a z-score. You should understand that connection here. Okay, and that we're transforming this non-standard normal curve to the standard curve of z-scores. So with that said, let's do our shortcut here. So second bar for the first question, normal CDF. I can use the x values. We're interested here that the pulse rate is greater than 100, so I'm going to type in 100 to infinity. So in essence, I'm kind of using the non-standard curve here. So 100 to infinity. But if I'm going to use the non-standard curve, I have to input that mean. And I have to input that standard deviation, 11.3. Okay, now I push enter. Same answer. Right, so that's pretty nice. Let's try the second question. Second var's normal CDF. On that one, we're interested in that it's less than 60. So I'm going to do negative E, 99, all the way to 60. And the mean is the same, and the standard deviation is the same as previous, so I'm going to leave those there. That's going to give me the left area, 0.1978. 0.1978. So that worked out. For the final question, 19, on slide 19, we want that the x values between 60 and 100, 60 and 100. Those are what they considered normal pulse rates. So we're going to go ahead and do that too. The lower here is going to be 60. The upper will be 100. Same mean, same standard deviation for pulse rates. And I get the same answer as well. So you see, you can do it that way. However, I think some of your questions will kind of have you do it and break it down using the z-score. But just you should know how to do it both ways. All right. Back to this again, right? So since here's one from chapter 4, the probability something significantly high if the probability of x or greater is less than 0.05. And something significantly low if the probability x or less is less than or equal to 0.05. Let's look at this question. Use the preceding criteria to identify pulse rates of women that are significantly low or significantly high. Based on dataset body data in Appendix B, assume that when women have normally distributed pulse rates with the mean of 74 beats per minute and a standard deviation of 12.5 beats per minute. So now, before we were doing males, right, so this is one about females. Okay, so we need the cutoffs, in other words. So the significantly high would be, we need these two values. So this is 0.05. I want not just the z-score, I want the x, right? But first I'm going to find the z-score, or we'll do it that way. We'll find the z-score, and then that'll be the significantly low cutoff, and then this side will be the significantly high cutoff. So that's what this question's asking. Find the cutoffs for significantly low and significantly high. Okay, so either way, we know we're going to use, what will we use here? Inverse norm or normal CDF? So if we can get this down, we'll be pretty good for today, for this chapter, really. That's the big question of all these questions. Inverse norm or normal CDF? Higher end, what do y'all say? Okay, so you might want to start this, or just kind of highlight this, or go back to it. But if you're given an area of probability and you want a z-score, you need to use inverse norm. So in this case, we are given an area of probability of 0.05, and we want a z-score. So we're going to use inverse norm. If you're given a z-score, and really, I guess I could put comma here. It's either a z-score or an x, right? Oh, and same right here. But if you're given a z-score and an x value, and you want the area or probability, use normal CDF. So here we're given a probability. The probability for the area is 0.05. Okay, so it's actually inverse norm. So we're going to do inverse norm to calculate. So let's do this. Second vars, inverse norm. Yeah, so on top of the two slides, before you jump into your homework, I would kind of internalize this, and it's going to go a lot faster for you if you just have that off memory. So internalize those homeworks about the left area, right area, area in between, and then also the inverse norm area, the keystrokes and all that. If you get that down, you get good with the calculator on those. Slide 20 and some of the other ones with the calculator keystrokes, I think you should have no problem with it. Okay, but yeah, inverse norm. So I'm going to do inverse norm of 0.05. So I get negative 1.645 for this z-score. I'm leaving a little bit space. So that means the other side we talked about earlier by symmetry is 1.645, right? So it's a positive. So I don't have to recalculate, but if I wanted to, I could do inverse norm of 0.95. Okay, but I'm satisfied with that. So here I can solve each of these in the z-score formula. So minus the mean is 74. Oh, equals, I should say. So the z-score is negative 1.645. X is unknown, minus the mean of 74, divided by 12.5. Okay, and hopefully you're okay if I do two things at once here. I'm going to need to multiply by 12.5, and after that I'm going to need to add by 74. I'm just going to do this. Negative 1.645, or 74. I'll do that first. 74 plus negative 1.645 times 12.5 equals 2x, right? By doing a little bit of algebra, multiplying by 12.5 right here, and then adding by 74. So let's do that. 74 minus 1.645 times 12.5. I get 53.4375. So 53.4 as our cutoff. For the significantly low, we'll do a similar thing for the right. I'm going to use negative 1.645 for the z-score, x minus positive. Oh, yeah, that should have changed there. This is positive, my fault. Positive 1.645, and then everything else is the same actually. And then we solve that, but it's going to be a similar process. You're going to multiply by 12.5 and then add by 74. So I'm just going to jump to it. So it's 74 plus this time positive 1.645 times 12.5 equals to x. And I'm just going to edit that, change it to plus. 94.6. So that's the cutoff for the top 5%. Okay, the top 5%. Okay. So now the shortcut, right? So here we've calculated, we did inverse norm of the area, 0.05. But can we get the answer directly without so much work? Yes. Just simply input the mean of this problem here, right? So 74 and 12.5. Okay. And then from there, let's see if it gives us what we want. It does. We get the 53. For the 94.6, we're going to have to think a little bit more, because if this is, remember, z-scores are only going to give you area to the left. So if I want area to the left here, the right of this is 5%, so the left of this is going to be 95%. So that's what I have to put for inverse norm. Second vars, inverse norm, 0.95. But that's it. After I think about that, the left area, it's going to give me that x value. Okay, so the cutoff here again was 53.4. And this one for the pulse rates, and the high pulse rates is 94.6 for the women. All right, so good. Yeah, and this is just more on the same. So we're just going to kind of do it with the calculator. So a student has an IQ. So find the, yeah, it says pulse rate, it should say IQ. Find the indicated IQ score. The graph to the right depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. A student has an IQ of 132. Is this a statistically high result? We can draw a picture, and keep in mind, I think this picture is not a question. We can make it a question. So we got to draw our own picture. Okay, so 100's the middle, right? So 132 would be maybe somewhere out here. And I'm interested in if it's a significantly high result, so I got to find the probability of x or greater. Probability of x or greater is 132. And I'm just going to find it. It's a normal CDF. without well, okay, let me do good practice. So x minus mu over standard deviation. We'll calculate the z-score. 132 minus 100 divided by 15. Okay, which save myself a little time. 132 minus 100 is 32 divided by 15. And I get 2.13. So the probability that x is greater than 132 is the probability that z is greater than 2.13, which now I can do normal CDF of the z-score. So this is the x-axis. The z-score would be 2.13. So 2.13 to infinity. Uh, 0.0165. Or 6 if I round. So that's the probability. But again, I could have skipped that and just did the mean and normal, or mean and standard deviation of this scenario. So I could have said 132 and beyond as the lower. So 132 is the lower. Upper would be infinity. The mean in this question is 100. And the standard deviation in this question is 15. If I do that, I'd get the same. So I get 0.0164. 0.0164. Which I'm not sure. Yeah, I don't think I have that here. No, I don't have that. That in other words, this input. Okay. So you might need to memorize that or come back to the video. Okay. So the second one is, oh, and then it asks, this is a question for y'all. Is this statistically high result right here? Is 132 IQ, is that a, he wants to know, that person wants to know if he's special. Is he statistically high? Why or no? Why or N? Yes or no? Okay, so good. So I got one answer. Jeremy says, yes, it's above 2 standard deviations. Okay, good. Good logic. Anybody have another answer for a different reason? Or I guess the same answer, yes, for a different reason. What's the other reason that this is statistically high? Greater than? I think you mean, but you're onto it, right? You mean less than, right? Because this probability right here, yeah, there you go. This probability is 0.0166, which is less than 0.05. So that's the other reason it's statistically high. Okay, so you want to kind of, internalize those things as well. Okay, so I think we're done with that question. Let's move on here. This one says, find the IQ of a person that's 84 or less. So we'll go 84 somewhere around here. We're interested in that probability. Okay, so we'll do the full deal. Want the probability that x is less than 84, which is equal to the probability. And I do this sometimes where I kind of do my work for my z-score in here. So in other words, I'm going to subtract 84 minus the mean is 100. divided by the standard deviation 15. And it's the same thing as I did before. I'm just doing the work in line. 84 minus 100, that's negative 16. So let's see, 84 minus 100 in parentheses divided by 15. I get negative 1.06. Now I just need to do normal CDF, so second Varsh normal CDF. From negative infinity to negative 1.06. Okay, and then I get an answer here. It's pretty low. Oh, no, that's not correct. Yeah, and okay, so again, let me tell you my thinking. I looked at this and I said, okay, that's a number pretty close to 0. And I looked at my graph and I looked at my picture. I said, it's small, but it's not close to 0. So I knew something was wrong. So that's how the graphs can help you, or one way the graphs can help you. So what went wrong was I'm using z-scores here in the lower and upper, but I didn't use the normal distribution, the standard normal distribution. Anytime you use z-scores, you should use mean of 0, standard deviation of 1. So here's the corrected, 0.1446. 0.1446. So in other words, about 14.46% of people have an IQ less than 84. And just as emphasis, you could have also used the shortcut I said, which is negative infinity to 84, the x value, right? We could have did this from the start with a mean of 100, standard deviation of 15. Okay, then we paste it and you get 0.14, same thing. Well, okay, you might notice it's not exactly the same thing. What's the reason for that? The reason is we rounded the z-score. Okay, but it shouldn't be so much of a difference to matter. Okay, so it's fairly close. That's 14.4%. This is 14.3%. All right. But if you want more accuracy, you can use more of these decimals here. Yeah, so I could have maybe used negative 1.0. Here, we'll try it one time. Let me bring this one back down. Okay, and I'm just going to edit it right here by adding more maybe 6s, and then we'll see if it comes a little closer. Yeah, so you see, that's the reason. It gets closer that way. Okay. Let's keep going. So here, okay, now these I think I'm going to kind of take, I think we've done enough of them. So we're just going to get answers. So the probability that x is less than 115 equals to normal CDF, second Varsh, normal CDF of 115 is the upper. Mean is 100, standard deviation is 15, so we're going to leave that there. 0.8413. Here, I want the probability that x is greater than 130. So again, we're going to do normal CDF, second Varsh, normal CDF of 130 to this time infinity. Okay, so that's going to be 0.0228. And then here we want the probability that we get between 85 less than x less than 115. Okay, so again, normal CDF, second Varsh, normal CDF of 85 to 115. I get 0.6827. Okay, so there you have it. Now, there is this picture here. Which I had a question to it, but I think I didn't have it properly there. But okay, so let me do this. Yeah, okay, we'll just draw it right here. I'm gonna draw it right here. So that question, you could have a picture like this and saying, okay, what's the for this distribution with an IQ of 100 and a standard deviation of 15, right? Mean of 100, standard deviation of 15. For that distribution, if you have a right area of 0.97, what cuts off the top 97% of this data? That's the question here. Well, again, the calculator only uses left area, which in this case would have to be 1 minus 0.97 is 0.03. So I'm given area, so I'm going to use inverse norm. So inverse norm of area 0.03 with the mean. I could do the z-score, and then I could use the formula and calculate the x, right? But this time I'm just going to do the formula, or I'm just going to do the shortcut, which is just type in the mean and the standard deviation, 15. And that'll get me the x directly. So the x for the pulse rate that cuts off the bottom 3% with the top 97% is 71.8. That's the pulse rate that cuts off, or not the pulse rate, sorry, the IQ that cuts off the bottom 3%. Okay. All right, so that should finish the work you need for this week's homework, over 6.1 to 6.2. But I'm going to go ahead and start on 6.3. And I might even post the next homework, but it won't be due till sometime next week. Okay. All right. So let's talk about sampling distribution. So we talked about normal curves. We're going to get into kind of this idea of sampling distribution. So it's a good idea. In statistics, what we try to do is find measurements. Like for instance, we maybe we want to understand the true mean of speed of a cheetah, right? To increase our understanding of cheetahs. It's not ideal to line up every cheetah in the world and have them race. It's probably not going to happen. So, but maybe I can get samples of cheetahs. And maybe I could get multiple samples of cheetahs and find their average speed. Now I would say that most of those samples, let's say samples of 5 cheetahs each, most of those samples are going to fall around the true mean of all cheetahs. There's going to be a few samples of 5 that might be extremely fast. And then there's also going to be there could be like this group of cheetahs that haven't made, and the pigs come to them, and they don't really have to hunt that much, so they're extremely slow, right? So that's possible, but the majority of samples of 5 cheetahs are going to have around the same average speed as the entire population. So this is called a sampling distribution. So this is a distribution of multiple samples of 5. In my scenario, 5 cheetahs, right? But the idea is that these sampling distributions of 5 cheetahs are going to be roughly normally distributed. The averages, or a distribution of the averages, is roughly going to be normally distributed, with most averages falling towards the true average, some averages falling above the true average, and some averages falling below the true average, and then some a little bit further away from the true average on the right and the left. Okay. In the same way, I could think of coin flips, and we understand that probability of a heads is 50%, and so I could have y'all do an experiment. And then you can flip 10 coins, and then everybody could report how many heads you got. So some of y'all might get 0.6 or 60% heads. Some of y'all might get 50% heads. The majority probably get 50% heads, right? Because that's expected. But it's possible some of y'all might get 60% heads. Fewer of y'all should get 70% heads. Some of y'all might get 40%, and then fewer of y'all might get 30%, and so on. It'd be pretty unusual to get 2 or 1 hits, but it is possible. Now, if my class size was a little bit larger, I would get kind of this shape if I did that. If I had everybody flip 10 coins, and we did the distribution, and everybody gave me the percents, and I created a histogram out of it, out of maybe 100 students, my distribution would be roughly normally distributed. So this is the idea behind sampling distribution. So with samples, in the case of the means, it said the 5 cheetahs. In the case of the proportions, it said the flipping the 10 coins. In this dealing with proportions, that's what p hat is, and p's. In this dealing with means, that's what x bar is. They're going to be roughly normally distributed. And not only are they going to be roughly normally distributed and centered at the true mean or true proportion, we're going to be able to calculate their standard deviations. And if we can do those two things, then we can calculate a z-score for this, and then we can calculate probabilities like in the previous section. Okay, so here's sample proportions of, I don't think they mention what it is. Okay, but this is an example of sampling proportions. Okay, I think more concretely, and I have this here. Let's see, do I have it open? I don't think so. Let me go to chapter 6. I'm going to get the script here for R. So here I get the text, and I'm gonna do some stuff here. This is available to you, so you have it there. But let's do. Let me just run this one real quick. Okay, I'm gonna copy and paste this. I'm gonna do this right now, but okay. There it goes. Okay. Okay, so I'm just going to copy and paste that. X and Y coordinates. Windows Cascade. Okay, here it goes. Yeah, so this is kind of a normal curve up there. But that's, yeah, okay. I just want to see if there's anything I want to talk about there, but no. Let's do the next one. Okay, so and instead of just copying and paste it, I'm gonna go ahead and type it out so I can talk about it too. So I'm going off of this here, but all right, let's talk about this. So we're gonna simulate dice. So here I'm gonna do x 1 to 6, and all that does is input 6 values into x, 1 through 6. Okay. Then what I want to do is create a sequence of numbers from 1 to 1,000. And this is a little bit on the advanced side, so you're not expected to know this, okay? But if you want to kind of play around with it, it's here. What I'm doing here is I'm trying to take samples from 1 to 1,000 by 1. So I'm going to take different amounts of samples. So and we're going to see what comes up. So in other words, like one sample would be a size 1, and then we're going to see how many 4s come up, right? That's the idea here. How many 4s come up? Okay. And you'll see when we generate this that n is just the numbers 1 through 10,000. Okay, so we're gonna take different sample sizes of our simulated dice. So we're gonna roll the dice a couple of times. So if I push X or random X or sample of X, okay, that's like doing a dice roll of 1. Okay, so that's a random dice roll, a single dice roll. I can keep pushing it, you'll see it comes up with different numbers. Sometimes it'll be the same number twice, but it's random numbers. So that's like a single dice roll. Okay. If I do 2, I can get 2 dice rolls, 1 and 4. I could even do the sum of that, right? But now, right now, I'm just kind of playing around with it. Then we'll get to the meat of this. So here, the sum of 2 dice. You know, if you ever lose your dice and you want to play your game, you can use R there, and that'll sum your 2 dice there. So this is a sum of 2 random dice. Okay, so now what I'm going to do is I want to go ahead, and I think actually I am going to copy this code instead of typing it in, because I'm looking at it and it's more than you need to know. Okay, so here I've created different numbers of simulations of dice rolls. So I'll explain from the top here. And I was interested, what we're trying to find is the number of 4s, the proportion of 4s, the percentage of 4s. So it turns out if I roll 1 dice, it happened to come to 4, right? Rolling 2 dices, we got 0 4s. 3 dices, we got 0 4s. 4 dices, 0 4s. 5 dices, it looks like we got 2 4s because 2 out of 5 is 40%. 6 dices, it looks here like we got 2 dices because 2 out of 6 is 1/3, which is 0.3. Rolling 7 dices, we got 0% 4s. Rolling 8 dices, we got 0.375. But then we're gonna kind of keep going. So that's what's going on here. Rolling 13 dices, we got 0% 4s. As I go down this list, maybe a little slowly, what do we notice like towards the end here? What do we notice towards the end? As the sample size increases, as my n increases, I start getting closer and closer to a particular number, right? So here I'm at 300. I'm kind of like at 70% 4s. At 365, I'm at 21% 4s. But then as I go on and on, if I roll the dice 701 times, I'm at 16.5%. Then what we start to notice is as I roll more and more, I start getting closer to 16%, 17%, 18%. But it still can vary a little bit. And as I get to 10,000, I kind of converge to 16.6%. And then if I do this, and I don't know if, yeah, maybe you'll understand this one a little better. Yeah, the histogram. So let me copy and paste this one. So here we'll notice that most of it's distributed at 16 point, or about 16%. But what is the 16%? It's 1 out of 6, right? This is our theoretical probability. So that's about 16.67%. And you'll see that most of them are distributed close to there. You have a few before, a few after, and not that many like too far out of there. But this one I like this graph here because this illustrates my next point. No, not that graph. There's more below this. This graph, okay. So let's try this here. This is a graph of what happens as the sample size increases. The red line is the probability of rolling a 4. Okay. So as I increase my sample size, you can see that at first there's kind of like a high variance between the sample, right? So this is maybe like a sample size of 100. But then as I go further along to sample size 200, it gets pretty close to the red line. And then as I get close to 10,000, I'm really close to the red line. So this is just an illustration of, as you increase your sample size, you're going to get closer and closer to the true probability of whatever proportion you're interested in or whatever mean that you're interested in. Okay, so that's what this illustrates. The larger your sample size, the closer you approach your proportion. And the histogram, that illustrates that your sample averages will kind of tend to be normally distributed. Okay, so that's what the histogram illustrates. All right, let me see if I have anything else there. No, not for now. Okay, so that's the simulation of rolling 10,000 dice. Okay, and again, you don't need to know too much of that or how to create that, but I'm just showing you. All right, more for the lesson. So getting thrown off here. That's PowerPoint. All right, so let's go back here. The sampling distribution is, again, the sample mean or sample proportions of size n taken from the same population. So all possible samples of size n, which turns out to be that there's a lot of size n of anything, as we'll see. So if there's 10, how many possible samples of 2 are there? 10 combination 2. So that shows you, we'll see here. So if there's 10 people in a population, or 10 persons, people, animals in a population, how many possible samples of size 2 can I get? 45. So there's a lot. But what's the sampling distribution is getting all those possible samples of 2 and finding the average, or finding the average maybe height of each 2 of them, and then plotting the averages on a histogram. But that histogram will be normally distributed. And same with the sample proportion. Okay, so P represents population proportion. P hat is sample proportion. So any like symbols are used with the letter as an X bar or P hat. Those are statistics, not parameter. Parameters tend to be Greek letters, with the exception of P. However, in some books you'll see population proportion as pi, but in this book they call it P. All right, so the distribution of sample proportions tends to approximate a normal distribution. Sample proportions target the value of the population proportion in the sense that the mean of all the sample proportions is equal to the population proportion. The expected value of the sample proportion is equal to the population proportion. This is important because what is the entire thing we're trying to do in statistics is we're trying to figure out, what is the percent of people voting for Trump, right? For instance, we want to calculate that percent. How are we going to calculate that percent? We can't literally sample every voter in the United States. That would be impossible or near impossible. So what's the next best thing is you take a sample of voters, get their p hats, and we're going to estimate p using p hat in that way. This is just an image of rolling. Well, here I say rolling a 5, but it's kind of what we did earlier. Okay. Just an image of that. And here again, it's kind of the same thing, but this is from the book, 10,000 Trials. So the sampling distribution of the sample mean, that's the distribution of all possible sample means with samples having the same size in from the same population. So the behavior of the sample means is it's going to be normally distributed, and also the sample mean targets the value of the population mean. And again, that's important because if we want a true mean of something, we most of the times we cannot get the true mean from the entire population because it'd just be unreasonable. For a small maybe class like your class, I can get a population mean, but for of whatever information I'm interested in, but maybe the average length of days that people are with this coronavirus, I probably couldn't sample every person with coronavirus, but I could take a sample of people that have the coronavirus, a random sample of people that have coronavirus, and I can estimate a true mean number of days of length that people endure the coronavirus using the sample mean. And then from there, estimate the true population mean. Okay, so here's just a small example. So it says a pediatrician has 3 patients with measles, and they are 4, 5, and 9. Consider the population 4, 5, and 9. If 2 ages are randomly selected with a replacement from the population, identify the sampling distribution of the sample mean by creating a table representing the probability distribution of the sample mean. So how do you create a? It turns out creating a probability distribution for this or a sampling distribution is kind of tough. This is just with 3. Okay, so 3 combination 2. Here, let me do alpha. 3 combination 2 is going to give us 3 there. Well, and actually this is with replacement, so I wouldn't even be able to do that. So you have to, if you're able to replace them, that's another story. So you can do 4 and 4, 4 and 5, 4 and 9, 5 and 4, 5 and 5, 5 and 9, 9 and 4, 9 and 5, 9 and 9. So if you get the averages of these, just add them up and divide by 2. Here's your averages. And what's the probability of getting each of these? Well, there's 9 outcomes, so each of them has 1 out of 9 probability. And if you remember, and here they just make it smaller because there's 2 answers with 4.5. So 4.5 actually has a 2/9 probability. And then what else? There's 2 answers of 6.5, so 6.5 has 2/9 probability. 7.0 has 2 of them, so also a 2/9 probability. And 9 is 1/9. So here we can calculate the mean of this right here. You can calculate the mean of this by using the probability distribution rules, which is you're going to multiply x times the p of x's. Yeah, so what's the population? This we could actually calculate, right? And if I do the true mean age, we can just add them up and divide by 3. So let's look at it. 4 plus 5 plus 9. Okay, divided by 3, that's going to give us 6. So that's the true mean age. Well, what do y'all think? Are the samples kind of close to that? I don't know. They're 4, 4.5, 7, 9. They're not really close for comfort. But now let's calculate this one. Let me see if I can. Yeah, so we can do 4. If you remember, you have to do your x times p of x's. So 4 times 1/9. Well, that's a third, not a 9th. 4 times 1/9 plus 4 times 2/9 plus, or 4.5, I should say. Times 2/9, 5 times 1/9 plus 6.5 times 2/9 plus 7 times 2/9, and then plus 9 times 1/9. Okay, so that's how you find the mean of a probability distribution. But look at that. So we actually got, if we took the mean of the sampling distribution, we actually got the so this is the result. The mean of the sampling distribution that I would write this way. So this is the sampling distribution of the size of size 2, gave us the true mean, right? The true mean being what we did. The true mean being 4 plus 5 plus 9 divided by 3. So here I have 18 over 3, which is 6. Okay, so that's 6. And so that just shows that the sampling distribution does estimate the true mean. Okay. Now, the sampling distribution of variances, well, that could be that tends to have a skewed distribution to the right. So variances can vary, and sometimes in a sample, one variance can be somewhat low, and then the very next sample, your variance will get very high. So R has a way, I can kind of use this idea of dice rolls, right? So then I can do samples of 5. So I could say sample dice rolls 5 times, okay? But I could also find the variance of that. So I can find the variance of my sample. R will calculate that for me pretty easily. Then I could do it again and again. Okay, and it'll give me different variances. Now we'll notice that some of them can be like pretty low, but then some of them can get up there. So now what I want to do, R allows me to do this, do the variance using this replicate function. It'll give me, here I have 100,000 variances. Okay, so I'll do 100,000 variances. And then I'm going to actually create a histogram out of that. This might take a little bit. Hopefully my computer doesn't. I mean, R is pretty efficient, but you never know. So I'm going to type in V here and then just show you what it did. So here's all the variances it calculated. Okay, but that's kind of hard to look at, just numbers, right? But you'll see some of the numbers get up there, like 5, 4.3, right, as compared to some of the ones we saw earlier. But you see this, okay? So you see kind of like a high point, and it kind of tails off. So if this was normally distributed, it'd kind of be cut off around here or here. But because it has this extra tail, this is kind of like a right skewed distribution. Okay, where the middle is here, but the distance to the end over here is one distance, and the distance to the end over here is a little bit longer. So that's a distribution of the variances. So the main takeaway is that variance is going to be skewed right. Okay, and that kind of illustrates that. Okay, and you won't have to create those the histograms of variances like that. However, I may have something coming down the line for you guys to create different histograms of project, but more to come. I'll let you know. Okay, so consider repeating this process, rolling a die 5 times, and find the variance S squared of the results. What do we know about the behavior of all sample variances that are generated as this process continues indefinitely? Okay, so In other words, we know that it's skewed right. Okay, that's really all we're interested in right there. It's skewed right. Variances will be kind of skewed right. And this is an illustration of that here. Okay, so an estimator is a statistic used to infer the value of a population, which is kind of what we've been talking about. We use like the sample, a random sample of voters to estimate the voters that will vote for Trump in the next election. Or we can use a random sample of COVID-19 patients to see the duration of in days that the virus lasts in them. So those are estimators of the population. So X bar is a good estimator of mu, the population mean, and P hat, the sample proportion, is a good estimate of P, the population proportion. Hopefully we have an unbiased estimator, which it targets the value that we're going for. So P hat is unbiased, X bar is unbiased, and S squared is unbiased estimators, which are good. That's unbiased is a good thing. Biased estimators are the median, the range, and the standard deviation. So sample standard deviations do not target the population standard deviation, but the bias is relatively small in large samples. So S is often used to estimate population standard deviation, even though S is biased of the population standard deviation. So in large sample size, you can overcome the bias of S, but it still has to come from a good random sample. Here, I think I'm going to kind of skip this part. Well, it's all here. It's not that we'll skip it. We don't have to generate it. But okay, so 4, 5, and 9 again. You do samples of 2 one more time. Then you find the range of these. So 4 minus 4 is 0. 5 minus 4 is 1. 9 minus 4 is 5. So forth. You get all these ranges, the probabilities of each of these. Okay, but what's the true range is going to be 9 minus 4. So we see that an individual sample is not really a good estimate of the range. And that's only 2, but just in general, it's not going to be a good estimate of the range. So what's the takeaway there? The range would probably be a biased estimator. Okay, so now to the real stuff, 6.4. It's all real stuff, but I'll tell you, I'll be honest with you, sometimes I skip this section, but it's important, the sampling distributions. But the main takeaway, because it does lead up to the next one, these ideas, but these are kind of general. Okay. All right, so let's move on. So the ideas are important, everything we talked about, but I guess really what I skip is kind of this sometimes. But it is important in terms of the understanding of sampling distributions of means. That's what it means to have a sampling distribution. But it gets kind of complex. That's just with 3, right? So it's if you had 5, there's going to be that much more samples. All right, so let's look at the central limit theorem. For all samples of the same size n, with n greater than 30, the sampling distribution of x bar can be approximated by a normal distribution with the mean mu and a standard deviation sigma over the square root of n. So this is kind of a big result here, thus called the central limit theorem, right? So this is saying if I had any distribution, given that the distribution, and I'm going to draw a couple of pictures here. Given that the distribution is normally, let's say the original distribution is normally distributed. Let's say in another population, there's a distribution of maybe wait times. In the hospital, uniformly distributed. Because I need to write this a little lower. Okay, and maybe another distribution that's skewed to the right. Okay, so what this is saying is if I take, let's say something I know that's normally distributed, heights. If I take random samples of people, most of their heights are going to tend towards the average, right? And maybe I should do this. This is the population. This is the distribution of X. We're going to do a separate distribution of the X bars. So most of the averages are going to fall around the mean, the true mean, which is right here, this whatever this is. Okay, some of the averages will fall a little bit above, and maybe a few, but for the most part, your averages are going to fall towards the true mean. But what's going to happen is that the curve up here will be a little bit tighter than the original population because these are averages, and averages tend towards the true mean. So these averages will tend towards the true population mean. Over here, the population mean would be in the middle as well. So even if your original population is uniform, if I get an average wait time, for instance, maybe from 0 to 5 minutes, most of them are going to be around 2.5 minutes. Most of the average wait times of, say, 10 patients is going to be around the average, the true mean. Some will be a little bit higher, like maybe 3 minutes average of 10 patients. Some might be a little bit lower, like maybe a 2-minute average of 10 patients. And then maybe some averages of 10 patients might go into 3.5 minutes, and some averages of 2 patients or 10 patients will go into 2 minutes. But again, even though the original distribution of wait times is normally distributed, if I get samples of 10 patients, I'm sorry, if the original is uniformly distributed, the sampling distribution of the average of 10 patients is going to be normally distributed. And again, a little bit tighter, right? So the data kind of gets squished in here rather than so spread out. Same thing with the skewed right. If the true, so here's the true mean here, but over here, skewed right, the true mean tends to be a little bit to the right of that would be kind of like the median right here. The mean is kind of a little bit to the right of that high point. So most of my averages will tend towards that. Some will be higher, some will be lower, but most of them are going to be pretty close. And again, the data is going to kind of be squished in. And in fact, not only do we know that it's not going to be as spread out, we actually know by what factor it's gonna kind of condense. So it's gonna be the same standard deviation divided by the square root of the sample size. So that's the central limit theorem, which is a pretty big result there. And so here is this is like your original data set, which looks kind of skewed right. But here's means of size of 100 from this population. If you take means of size 100, most of the means are going to actually fall towards the true mean, which the true mean here would be about 60, which is that high point, or close to that high point there. But these are averages of this population. And so you can see it kind of tends towards a normal distribution. So this is what we call a sampling distribution of size 100. This kind of says the same thing. We'd want to check requirements. One of the requirements is the original population is, if the original population is not normally distributed, then n is less than or equal to 30, but the distribution of X bar might not be approximated by a normal distribution. So, and I don't think we'll be able to get into any questions yet, but that's going to be one of the main things. Is the original population normally distributed? If yes, you can use these approximations, or you can use these results for the central limit theorem. If it's not normally distributed, The next question is the sample size large enough? In other words, is the sample size greater than 30? So 30 is this kind of magic number where we say it's large enough to use the central limit theorem. Okay. Then from there, we have the notation, but I think we're going to have to kind of cut it off there because I don't think we'll. Well, here's one for your homework. Since I got a minute, it won't take me long. Basically, this is from last class, that x is greater than 8, or the last section. We know how to do that, calculate a z-score. Here, the only difference between this question, this is one randomly selected person. This is the probability of 16 randomly selected person greater than 80. So on B, the only difference there is I'm going to use the z-score of z-score of x bar minus mean over the standard deviation over the square root of n. So x bar being that I want to know what's the probability that a sample of 16 has an average of 80. So I would do 80 minus the mean divided by the standard deviation, which is 12.5, over the square root of the sample size 16. And then calculating that real quick. And I'm only doing this just because if some of y'all want to kind of get ahead on the homework, you'll be able to, I think, just with this one tidbit. Here, so we'll do 80 minus 74 divided by, I put my parentheses, 12.5 over the square root of 16. Right, or out of that, close my parentheses, I get 1.92. So 1.92, that's my z-score of interest. I got to find that probability of 1.92 and beyond, which is just normal CDF. So second vars, normal CDF from 1.92 to infinity, which we'll find to be 0.0274. Okay, so that's the probability that x bar is greater than or equal to 80, is the probability that z is greater than 1.92, which is equal to 0.0274. So that's which if I do let's see, yeah. So if I do without. Right, if I do question A, it's going to be almost the same thing, but 80 minus, this is from before, 80 minus 74 divided by 12.5, which is, what, 6 over 12.5, 6 divided by 12.5. And that's 0.48, so that's the probability that Z is greater than 0.48, which is equal to normal CDF of 0.48 and beyond to infinity, okay, which gives us 0.3156. So there's a lot greater chance that an individual has greater than 80 heartbeats per minute than 16 people to have an average of 80 heartbeats per minute. And that's what the central limit theorem says. So you really kind of study the difference between A and B. That should kind of get you started if you want to on the next homework section, but I'm going to go ahead and make it available since I started this section. However, it's not due yet. Okay, well, I wanted to make that point because we took a long time. And given that part B involves a sample size that is not larger than 30, why can the central limit theorem be used here? On B, we can use the central limit theorem because it says normally distributed, even though the sample size is only 16 and not 30. Okay, but that's on C, I mean. Okay, well, I'm going to go ahead and end it there. Y'all have a good rest of your week. If you have any questions, feel free to email me, or you can stick around after class, after I turn this video off.